Hello, everybody. We are done with the quantum mechanics section of the first part of this course, fundamental physics. In this and in the next lecture, I would like to tell you something about the crystal structure of solids, elements of crystallography, because most semiconductors which are commercially relevant are crystalline semiconductors. There are also amorphous semiconductors, but they will not be part of this lecture series. In this lecture, I will introduce the most important concepts of crystallography, the concept of Bravais lattice, and I will list the Bravais lattices in 3 dimensions. Next, I will introduce the concept of the primitive cell and the unit cell, how they differ. Then I will tell you what crystal structure really means, not just Bravais lattice, but also the basis of the crystal structure. And then I will say a few words about cubic structures, and as one special type of cubic lattices, the diamond lattice and the zincblende lattice. And then also I will tell you how diamond lattice is formed from the point of view of quantum mechanics. All right, so Bravais lattices were constructed in the mid-19th century by a French crystallographer, Auguste Bravais, who thought about possible ways of arranging lattice points in space. Now, a lattice point is understood in the same way it is understood in geometry. That is, it is a structureless, dimensionless unit, infinitely small point in 3-dimensional space. So we want to arrange them periodically. That is, this arrangement must possess translational symmetry. If you take this whole lattice and shift it in a particular direction by a particular distance, this lattice, the shifted lattice, will superimpose with the original lattice. This is what we mean by the translational symmetry. So every point of the Bravais lattice can be described as a linear combination of 3 translation vectors, which we denote as A, B, and C. And the coefficients in this linear combination, I, J, and K, are integer numbers. So A, B, C are translation vectors, and any lattice point is a linear combination of A, B, and C with integer coefficients I, J, and K. In addition to this translational symmetry, lattices, crystal lattices, may have what we call point symmetries. And point symmetries involve rotations. So you rotate the whole lattice around a particular axis. For example, this axis may connect this lattice point and that lattice point. You rotate by a certain angle. And as a result, the lattice is rotated into itself. The new lattice points are in the same positions as the old lattice points. Then we have inversion, where the coordinate of each lattice point is replaced with its negative. Then we have reflections. You select a plane in the lattice and you reflect each lattice point relative to that plane, and this becomes a symmetry operation if after such an operation the lattice gets superimposed, the new lattice gets superimposed with the original lattice. And then we have rotation inversions, which are combinations of rotation operations and followed by an inversion. Now, all these 4 types of symmetry operations are called point symmetry operations because when you perform them, one particular lattice point remains where it was. Okay, so you perform all these operations such that one, for example, inversion is performed relative to a particular inversion center. Now, because the point symmetry operations must be consistent with the translational symmetry of the lattice, translational symmetry is in a sense like the most fundamental property of crystalline lattice. And whereas the point symmetry operations, they may or may not be there. But every crystal lattice has this translational symmetry. So in order to be consistent with the translational symmetry, the rotations, not all of those point symmetry operations are allowed. So in particular, rotations cannot be performed by an angle, let's say 1/5 of 360 degrees. That would be 72 degrees, or 1/7 of 360 degrees. The only allowed rotations are by 360 degrees, but that's trivial. That's like not doing anything at all. Then we have 180 degrees, 120-degree rotations. That is 1/3 of a full rotation. 90 degrees, 1/4 of a full rotation, and 60 degrees. All right. So, and this requirement that point symmetries must be consistent with the translational symmetry limits the number of all possible Bravais lattices to a relatively small number. So in particular, we have only 7 families of such lattices. So the families are distinguished by the fact if the lengths of these 3 translation vectors are all the same, or maybe 2 translation vectors have the same length and the third one has a different length, or maybe all 3 translation vectors are different. And also the angles between the translation vectors, which can be arbitrary. So in particular, if all the angles between the 3 translation vectors are arbitrary and the translation vectors have arbitrary lengths unrelated to one another, then we have the least symmetric lattice of all. It is called the triclinic lattice. Other values, there are also the special values of the angles between the translation vectors, which are 90 degrees and 60/120 degrees. Okay, so, and depending on these combinations, there are not that many combinations. It turns out that there are only 7 combinations. We have 7 different families of crystal lattices, starting with the least symmetric triclinic lattice without any special relation between the angle and the translation vector lengths, and ending with the most symmetric family of lattices, the cubic family. Now, in each family, you can have at most 4 members, and those members are produced by adding an extra lattice point or extra lattice points, and you add those lattice points. You can do this in 4 ways. So the first way is not to add lattice point, an extra lattice point, in which case the unit cell of that lattice, by the way, these are the unit cells, right, in this diagram. So if you do not add an extra lattice point, then the unit cell can be called the primitive unit cell or the simple unit cell. So primitive cell is more conventional word. You can add an extra lattice point right in the middle of right in the geometric center of the cell, in which case the cell becomes base-centered. No, not base-centered. Sorry, scratch that. Body-centered. If you add an extra lattice point right in the middle of a unit cell, the unit cell becomes body-centered. Then you can add 1, 2, 3, 4, 5, 6 extra lattice points in the middle of the opposite faces, in which case the unit cell becomes face-centered. And finally, you can add an extra lattice point, 2 extra lattice points on the 2 opposite faces of the unit cell, but not on the remaining 4 faces. So just on the 2 opposite faces, the bases of the unit cell, in which case the unit cell is called base-centered. Now, it may happen that adding this extra lattice point in the middle of the unit cell or on the faces, does not result in any new symmetry. So does not result in a new. So for example, if you take a triclinic lattice and add an extra lattice point in the middle of this triclinic unit cell, then you will still add up the same old triclinic unit cell. So the adding this extra lattice point doesn't create anything new. Okay, so only those additions of extra lattice points that produces new lattices, they count. And in this way, some of the lattice families become consisting of several members, at most 4. Cubic lattice family consists of only 3 members: primitive, cubic, body-centered, and cubic face-centered. All right. So the building block of a Bravais lattice is a unit cell. A unit cell is a collection of a group of lattice points whose periodic repetition, whose by means of translation, by a translation vector, generates the whole lattice. The choice of a unit cell is not unique. So these are the 2-dimensional lattices. With the unit cells, this one and this one, gray areas in this 2-dimensional lattice are all unit cells. And so the choice is not unique. But then, of course, you want to keep the unit cell as simple as possible and preserve the symmetry of the lattice to as closely as possible. Now, a unit cell of the smallest volume is called the primitive cell. The primitive cell contains only 1 lattice point, whereas an arbitrary unit cell may contain as many lattice points as you want, and in fact, an arbitrary unit cell may not have the symmetry. So, for example, in a 2-dimensional lattice, a unit cell could consist of 2 squares. This is a square lattice in 2 dimensions. A unit cell may consist of 2 squares, put one at the other, sharing the same, sharing one side. Now, there is a special choice of a primitive cell which preserves the symmetry of the lattice, and this is the so-called Wigner-Seitz cell. It is defined as a collection of points in space which are the closest to a particular lattice point than to any other lattice point in the lattice. So here I wrote Wigner-Seitz cell is a primitive cell whose surface is closer to a given lattice point than to any other lattice point, but probably this is not, I just needed some space on this slide. So what I meant was that the region enclosed by that surface is closer to a particular lattice point around which the Wigner-Seitz cell is built. But writing that down would take an extra line, as you see, the slide is already pretty dense. Now, how to construct the Wigner-Seitz cell? The procedure is simple, unique, unambiguous. So you focus on a particular lattice point. You connect that lattice point to all neighboring lattice points with straight lines. And each of these connector lines is divided in half by a perpendicular plane. So you will get a bunch of planes. And the space enclosed by those planes is your Wigner-Seitz cell. So here is the procedure illustrated on an example of a 2-dimensional lattice. So you focus on this red lattice, on this lattice point. Here are its neighbors, 1, 2, 3, 4, 5, 6. 6 neighbors. Connect a given lattice point with the neighbors, divide by, well, not by planes, but in 2 dimensions, that would be with lines, perpendicular lines, right in the middle. And this is your Wigner-Seitz cell. So that's how it works. Now, Just specifying the Bravais lattice is not enough. You also need to tell what kind of atoms are attached to every lattice point, how those atoms are situated relative to one another, how many atoms there are. So this information is called the crystal basis. So the crystal basis consists of one atom A located like at the origin, and the origin is taken to be a particular lattice point. Then there are two atoms B located like one to the left, the other one to the right at such and such distances, such and such radius vectors. So this is the basis, and the crystal structure is it tells you two things. It tells you the Bravais lattice type of a crystal and the crystal basis, that is what kind of atoms and where they are in each unit cell. So for example, okay, so here are three examples: copper, sodium chloride, the usual table salt that you use in the kitchen, and diamond made of carbon atoms. All these crystals form face-centered cubic Bravais lattice. So here is the face-centered cubic lattice. The conventional unit cell is a cube with extra six lattice points on the opposite six faces of the cube. This is the face-centered cubic. Now, copper is just the face-centered cubic lattice. In each lattice point, you have a single copper atom. Sodium chloride is the crystal structure of sodium chloride is two interpenetrating FCC lattices. So imagine two FCC lattices of the same lattice constant. One is made of sodium atoms and the other made of chlorine atoms. And initially, you make them coincide. So each sodium atom and each chlorine atom occupy the same position. So the two FCC lattices perfectly coincide. And then you shift one of these lattices, let's call them sublattices. Then you shift one of those sublattices, let's say the chlorine sublattice relative to the sodium sublattice, relative along the edge of the cubic unit cell by 1/2 of its length, and that's your sodium chlorine lattice. Diamond lattice is also made of two interpenetrating FCC lattices. I will tell you about the diamond lattice in the next slide, or two slides from here. Now, we also introduced the parameter called atomic packing fraction. Atomic packing fraction tells you how densely the atoms are packed with each other in a crystal lattice. And the atoms are viewed as solid spheres, such that the neighboring solid spheres just touch each other. They do not overlap. There is no space in between. They're like billiard balls that are touching each other. And then you divide the volume of the solid spheres by the total volume of the crystal. So you can actually focus on a single unit cell, and you identify. So here are the atoms which are in my unit cell. I model them as solid spheres. Those solid spheres have such and such volume. The total volume of the unit cell is the cube of the lattice constant. I divide one by the other, and that's our atomic packing fraction. So now I will discuss the basic cubic structures. As mentioned earlier, there are three types of cubic lattices: the simple cubic lattice or the primitive cubic lattice. It has just one atom, or one lattice point per unit cell. Now here is the unit cell of a simple cubic lattice. And at the first glance, it may seem like, no, hold on. It's a cube. The cube has 1, 2, 3, 4, 5, 6, 7, 8 corners. And in each corner, we have 8 lattice points. So probably it is 8 lattice points per unit cell. So no, it's not 8, it is just 1, because each of those 8 corners is shared by exactly 8 unit cells. So each corner contributes 1/8 of a lattice point to a particular unit cell. And because of that, because we have just one unit cell per, let's say you have one atom in each corner, each unit cell, it is a monatomic crystal. So one atom per lattice point, then the concentration of those atoms would be simply 1 divided by the volume of the unit cell, 1 divided by the lattice constant cubed. It's 1 atom per unit cell. Atomic packing fraction is pretty small. It is only 52%. So if you model this atom with solid spheres, then the spheres would only occupy slightly above half of the volume of the total crystal. Simple cubic lattices, simple monatomic cubic lattices are almost never found in nature. There is only one material that crystallizes into a simple cubic lattice, and this material is polonium. It's like in the very end of the periodic table, a radioactive element discovered by Marie Curie, polonium. All right, so now let's move on to body-centered cubic lattice, which is the primitive cell of the body-centered cubic lattice is not a cube, but the unit cell is a cube. So the unit cell of a primitive, the unit cell of a body-centered cubic lattice is a cube with an extra lattice point right in the middle. And the primitive cell, which has only one lattice point, is constructed by, so connect the corner of this conventional unit cell with the lattice points in the middle of 3 adjacent conventional unit cells that share that corner. You will get 3 vectors. And based on those 3 vectors, you can build a parallelogram. And that parallelogram is the primitive cell of a body-centered cubic lattice. All right, now, but the conventional unit cell, which does possess an obvious cubic symmetry, has 2 atoms. If we attach an atom to each lattice point, so again, we assume that the lattice is monatomic, and attach a single atom to each lattice point. So the 2 atoms come from, okay, we have 8 corners. Each corner atom is shared by 8 unit cells, so contributing 1/8 of its volume to a particular unit cell. So 8 times 1/8 is 1, plus an extra atom right in the center of the cell. So 1 plus 1, 2. So the concentration of atoms in a BCC lattice would be 2 divided by the lattice constant cube. And many atoms, many metals like to form body-centered cubic lattices. The atomic packing fraction of a BCC lattice is 68%. Now the face-centered cubic lattice is can be viewed as a cube. The unit cell of a FCC lattice is a cube with 6 extra lattice points situated on the 6 opposite faces of the cube. Now, the conventional unit cell of an FCC lattice has 4 atoms. Now let's count. So the corners contribute the 8 corners contribute 1/8 of their volume, giving us 1 atom attached to each lattice point, 1 atom per unit cell. And then we have 1, 2, 3, 4, 5, 6 extra lattice points with an atom in each. And each of those atoms is shared by 2 unit cells. So each of those atoms contributes 1/2 of its volume to a particular unit cell. So we have 6 divided by 2, 3 atoms from the faces, plus 8 divided by 8, 1 atom from the corners, giving us total 4 atoms, 4 lattice points per unit cell. So the concentration of atoms is 4 divided by 8 cubed. And the atomic packing fraction for an FCC lattice is the largest one of all, 74%. There is only one lattice which has this high atomic packing fraction, as high as 74%. It is the hexagonal lattice. Now, the primitive cell of any Bravais lattice must contain just 1 lattice point, and the primitive cell of an FCC lattice is constructed by, so draw 3 vectors from the corner of a unit cell, which is to the left, the conventional unit cell, to the centers of the 3 adjacent faces, square faces, which share that corner. Now you have 3 vectors. Build a parallelogram on these 3 vectors. That will be your primitive cell of an FCC lattice. Okay, now a little bit more complicated lattice is diamond lattice. Diamond lattice can be understood as 2 FCC lattices, as by the way I have mentioned earlier in one of the previous slides. So imagine 2 FCC lattices which originally superimpose. So the lattice points of one FCC lattice are in the same locations as the lattice points of the other FCC lattice. Now you shift, let's call them sublattices, FCC sublattices. Now you shift one sublattice relative to the other, without rotation, of course, along the main diagonal, the longest diagonal, let's say this one, start here and here, by 1/4 of its length, of the length of this diagonal. So the length of the diagonal is a, the lattice constant, a square root of 3. And you shift along this diagonal by the distance a square root of 3 divided by 4. And as a result, you will get diamond lattice, diamond structure. Now, atomic packing fraction of diamond lattice is quite low. It is only 34%, even smaller than in simple cubic lattices. Examples of the lattices with diamond structure are silicon, germanium, diamond itself, alpha tin below 13 degrees. It turns out, I didn't know that, but it turns out that tin has this diamond structure below 13 degrees. And now zincblende structure. So diamond structure is formed when the 2 sublattices are made of the same type of atoms, for example, carbon, silicon. Zincblende structure, such as zinc sulfide, which is zincblende, or gallium arsenide. A zincblende structure is formed when the 2 sublattices, 2 FCC sublattices, are made of different atoms. But the procedure is the same. You shift one sublattice relative to the other along the main diagonal of the unit cell of an FCC lattice by 1/4 of its length. Here we talk about zincblende structures. All right, okay. Okay, so many semiconductors which are relevant in industry, here are some examples, like silicon, of course, the most important one of all, and then other semiconductors. they form either diamond or zinc blende structure due to for chemical reasons. Not all semiconductors are diamond or zinc blende. Exceptions exist, but for example, silicon carbide, even though silicon and carbon belong to the same column in the periodic table, they do not form a unique crystal structure. They form like this number is impressive, about 250 different crystal structures called polymorphs or polytypes. All right. So the last piece of information, I believe this is the last slide. Yes, this is the last slide. How diamond structure is formed. It is formed via the process called sp3 hybridization. So here is the thing. So let's atoms that find themselves in group 4 of the periodic table have 4 valence electrons. 2 of those valence electrons exist in the s orbital. An s orbital looks like a sphere. So this representation, if you want to visualize an orbital, it is like the most convenient way to visualize an orbital is like to show how the electron cloud is distributed. And an s orbital is spherically symmetric. So, and then you have three orbitals of p type, 3 p orbitals. 2 other electrons exist in those p orbitals. Now, the 3 p orbitals look like dumbbells, okay? And they are orthogonal to each other. Like you can orient them, one along the x-axis, one along the y-axis, and one along the z-axis. So 3 p orbitals, and two of which orbitals are occupied by electrons. I guess you can have 2 electrons in a single p orbital with opposite spins electrons. The energies of the s and p orbitals are practically the same because, as you remember, from the theory of these are hydrogen-like orbitals, and from the theory of hydrogen atoms, we know that the energy depends only on the principal quantum number, that is, which labels the shells, but not on the orbital quantum number and not on the magnetic quantum number. Well, actually it does, but approximately this effect, like they have approximately the same energy. To find the energy dependence, how the energy of a quantum state depends on the orbital and magnetic quantum numbers, you need to include like extra effects which we have neglected, like spin orbit coupling. But okay, that doesn't matter. All right. Now so that's for a single, let's say, silicon atom. You have 2 electrons in the s state and 2 electrons in 1 or 2 of the remaining 3 p orbitals. Now you bring those silicon atoms together to form a crystal. And it turns out that it is energetically more favorable for the s orbitals and the 3 p orbitals to combine into the so-called sp3 hybrid orbitals. The sp3 hybrid orbital looks like, what does it look like? Like a balloon, like a baseball bat, right? And those baseball bats become, they point from in each atom, they point from the nucleus to the corners of a tetrahorn. Okay, at an angle of 109.5 degrees relative, like with each other, with 3 tetrahedral orbitals. And now each sp3 orbital is occupied by a single valence electron. But due to spin, orbitals love to have two valence electrons with spin up and spin down. So the sp3 orbitals share electrons with the neighboring atoms. So a given atom has own electron in a particular sp3 orbital, and it shares an electron with a neighboring atom, so that now each sp3 orbital is occupied by two electrons of opposite spins. So those sp3 orbitals become bonds. They are directed. They point from the nucleus of each atom in the directions, like in the corners of a tetrahedron, and those tetragonal blocks become the building blocks of a diamond structure. Now, so this binding is purely covalent. This bonding is purely covalent. In zinc-blende bonding, the situation is slightly more complicated because zinc-blende crystals are formed by atoms which belong to group 3 and group 5, or group 2 and group 6. So let's say group 3 and group 5, like boron nitrate. Yes, it's group 3 and group 5. No, okay, let's take not boron nitrate, gallium arsenide. Let's take gallium arsenide. Gallium is from group 3 and arsenic from group 5. Now, group 5 atoms have 5 valence electrons. Group 3 atoms have 3 valence electrons. So a group 5 atom an extra valence electron is transferred from group 5 to group 3. So now both types of atoms have 4 valence electrons, and now they turn into a positive and the negative ions respectively. And then the bonding mechanism proceeds via this sp3 hybridization mechanism, as I just described. And also there is a little bit of ionic bonding because, like I said, the two atoms, group 3 atoms become, like gallium atom becomes negative, slightly negative, and arsenic atom, group 5, becomes slightly positive. So zinc-blende structure is partly covalent, but also partly ionic. So I think this is the last slide. Yes, it is. And that's all that I wanted to tell you today. Thank you all very much for your kind attention. I'll see you next time.